Hello everyone, I'm Dr. Shanti Krishnan. I'm an academic in the School of Engineering at Swinburne University of Technology. My area of interest spans from nuclear engineering to electronics to digitalization. I have founded the first Industry 4.0 test bed at Swinburne University of Technology. My research areas is digitalization in the area of space and mining. Today, we are going to talk about digitalization for decarbonization, how we can leverage technology for a sustainable world. So, we will start with introduction to decarbonization, talk about the role of digitalization, then key technologies and case studies, challenges, and future outlook. Decarbonization is reducing carbon dioxide and greenhouse gas emissions to combat climate change. As we all know, Australia's commitment is net zero emissions by 2050 and 43% reduction by 2030. This is as per the Climate Change Act 2022. The net zero market is an ecosystem of industries, technologies, and services driving decarbonization. And the key sectors that we will be talking today is energy, manufacturing, transportation, medical, and healthcare. We'll see how the key sectors can leverage digital technologies in moving towards decarbonization. The findings and results that we will discuss today in the use cases are based on real-world industry projects undertaken by Swinburne University of Technology for the most part. We will also see how applied research can translate into industries. So what is digitalization? Digitalization is digital technologies to transform processes, systems, and services across various sectors to enhance efficiency, accessibility, and innovation. It actually leverages a confluence of multiple technology sets like AI, artificial intelligence, augmented reality, cloud computing, additive manufacturing, and so on and so forth. It is really a real-time intelligent integration not only of machines but humans and objects as well towards a management of systems.
From my perspective, digitalization is a using of digital tools, models, and the simulations to improve the efficiency of the production processes or product. It includes practice like simulation, system engineering, digital tool development, and data integration as well. In a manufacturing context, it enables faster and more informed decision making, reducing reliance on trial and error, and allows us for more agile and data-driven production systems.
Digitization means it's a proper communication, machine to machine, machine to people, in a more, what would we say, more customized way, I would say.
So let's start with an interesting question. All of us now are using generative AI, right? So what is the carbon footprint for a simple question such as, is net zero a myth? It actually draws about 0.3 to 0.5 watt hours of electricity. This is roughly equivalent to the energy used to charge a smartphone for a couple of minutes or a microwave for a few seconds. However, generative AI and digitalization is an integral part of our society. Key sectors and the energy consumption, let's talk about it a bit. First is energy, which is taking about 40% of the global emissions. The challenges are that coal and gas dominate 60% of the electricity. Data centers for digital tools like AI and IoT consume 1 to 2% of the global power, projected to hit about 9% by 2030. How can we move towards net zero? It is achievable through aggressive renewable adoption and storage, which is batteries. The next sector is manufacturing, which consumes about 30% of the emissions. The challenges are high emission processes in cement and steel. So the net zero outlook will be to use digital twins and automation to cut down waste. Innovations such as green materials, such as green steel, green cement, and green hydrogen will also play an important role. Transportation, it's very difficult to have electricity driving the aviation and shipping. So one of the things that people are going for today is biofuels, although it is expensive. So electric vehicles make road transport possible, and digital logistics increase data center energy. So we need to weigh at all times a balance to get less carbon footprint as much as possible. Healthcare, 4 to 5% of emissions. The challenge is the hospitals use 24/7 energy. They use single-use plastics, which are hard to replace. Supply chains for medical sector rely on high carbon pharma and devices. Opportunities that we have is to use telemedicine to cut travel emissions by about 80%. Use renewables, use reusable devices, and digitalization to reduce waste and inefficiencies. Where does digitalization fit in the product life cycle of the value chain? Digitalization would fit right from the beginning in the R&D stage, where it can be used to detect clashes between components, assess the ergonomics, and simulate the product behavior even before the product is made. Then we come to the production. As the products are updated and adapted, digital twins and digitalization in general, smart sensors can be used to aggregate information, which can be analyzed to identify the usage. More importantly, it is very useful even at the end of life when a product is no longer required by the user. We can use digitalization to guide appropriate end-of-life actions. Material data can help to determine appropriate recycling and waste streams. We hear a lot about recycling. With digitalization, it becomes more possible to validate the claims of recyclability. It seamlessly performs the horizontal integration across the entire value chain. Some of the most important key digital technologies for decarbonization include smart sensors and Internet of Things, including smart grids and energy monitoring systems, artificial intelligence and machine learning for predictive maintenance and demand forecasting, and digital twins for optimizing the industrial process. We will see how these digital tools are applied in a number of use cases. Before we go there, let us first try to understand what a digital twin is. The digital twin is a working virtual model of a product or a system across its life cycle. It accurately portrays a system and also the environment in which the system is working. If I may say so, it forms the heart of digitalization. Now, after having talked about digitalization in general and its importance, let's see some of the applications and use cases as we have experienced it at Swinburne University. We are standing in front of an industrial cyber-physical factory system. Now, this cyber-physical factory system is a completely automated system which runs off-grid completely on solar power. It consists of 4 automated systems. One is the first one, which is the storage and retrieval system. There is the drilling station, followed by a robot cell which assembles a product. The product that's being assembled by the system is the assembly of a smartphone. Today, we are interested to see how real-time energy monitoring is being done from this completely off-grid solar-powered cyber-physical system. Cyber-physical factory system integrates the physical manufacturing processes with digital monitoring and control. It features programmable logic controllers. 2 programmable logic controllers manage the energy monitoring and the robot cell energy monitoring connected via a central gateway. The gateway acts as a central hub linking these controllers and facilitating data transmission to the cloud. Cloud enables data storage and remote access for the system. So, we are monitoring the power and the air pressure from both the cyber-physical factory robot cell and the total power of this entire system. We have used a 240 volts microgrid power supply using a solar system. The solar power generation slide here shows that the 200 volts DC is taken from the photovoltaic cells and it generates 240 volts for the microgrid. Now this 240 volts charges the batteries from the microgrid during the periods of low demand and it supplies power to the microgrid when the PV inverter is unable to meet the demand. It also is used for powering the CP factory in this way. The energy consumption for the CP factory is 459 kilowatt hour and for the robot assembly cell is 370 kilowatt hours. One thing to bear in mind is that currently the CP factory is running in an idle mode. There are no parts being manufactured and this is the energy consumption. What we should not forget is the compressed air pressure. The gauge is measuring about 0.592 for megapascals for the CP factory and 0.490 megapascals for the robot assembly cell. Thus, this particular setup, this real-time energy monitoring system can be used to monitor the power and the energy totals, and we can actually optimize the energy usage by identifying high consumption periods and reduce waste such as during the idle states. Now let's look at how it can be used for predictive maintenance. You can see from the graph that 1 liter per minimum is the airflow that is being consumed by the robot assembly cell. What does it mean? It is actually equivalent to 1 Coke can full of compressed air being used even when the robot assembly is not doing any job. So this shows the trends to detect leaks and inefficiencies, preventing energy loss. Scenario planning, we can use all of this information to calculate the worst case scenarios, the maximum power being drawn to ensure that the microgrid or the backup systems can handle the peak loads. What should be the size of the battery in order to be able to cater for efficient and continuous running of the system? So solar cells and batteries are part of this microgrid. Off-grid scheduling, determine the best times to operate off-grid by correlating low consumption periods, that is the idle robot, with available stored energy. Thus, all of these predictions, digital predictions, can be used to make informed decision making easy. Swinburne University of Technology undertook a project with Lifeblood Red Cross to determine if digitalization would be more effective in throughput optimization and reducing waste and inefficiencies. What you see in front of you is a digital footprint of the processing line which processes the whole blood bags. Essentially, the whole blood bags from the donor center arrive at the processing center. This is centrifuged, followed by filtration to isolate the whole blood into its components, which is the plasma, the platelets, and the red cell. The critical component in this is the something called the automated separators, which separates these blood components. An effort was made to identify the waste and inefficiencies in the system, which is continuously evolving and emergent. Now, medical manufacturing is a source of high carbon footprint. It is not possible to go net zero as it is a life-saving and a critical industry. And continual improvement, therefore, is an integral part of the system. Now, in the coming slides, we are going to see how digitalization has been used to identify the waste and inefficiencies in a virtual environment using the digital twin. So, a throughput evaluation was done using a digital twin. Let's recap again. Digital twin is a replica of the physical system, including the environmental parameters. And what we found was that in the current system, there are 18 blood separators that are being used. And the throughput per hour generation, as you can see, is 107 for plasma, 107 for red cell, and 96 for buffy coat, which is the pooled platelets and the white cells. Next, we created a scenario by reducing the number of separators to 12 separators just in the virtual environment. And as you can see, the throughput remains the same. So what does it prove? It proves that 2 separators in each of these 3 lines are redundant. So from 18, we have gone to 12. And this has resulted in reducing the waste because, as you have seen before, when an equipment is idle also, it was drawing air in the CP factory. The next thing was to determine the operator utilization. This is again a digital twin output, as you can see here. And it was found that the operators were working only for 65% of the time. That was the value at time that was from the operators. So this data-driven information can be used by the decision makers to optimize the throughput, reduce waste, and optimal resource utilization. The other thing that is possible is to test scenarios to meet the variable demand and supply. What I mean by that is, if the supply is not high enough, it is not necessary to run the machines at full operational speed and thereby reduce the energy consumption. So all of these scenarios can be tested using digital twin before being applied to the real system. The other problem issues that we have with critical manufacturing, such as the lifeblood Red Cross processing line, is that you cannot stop the system to test the various scenarios. We'll see in a minute about that. Okay, now for just-in-time production, what we see here is an intelligent warehousing system which we have built at Swinburne University, and which is a model because it can accommodate products of different sizes and shapes. So the current smart warehouses are rigid, expensive, and proprietary, limiting the SME adoption and wasting resources on new builds. A modular AI and IoT-driven system that adapts to diverse needs and upgrades legacy setups, reducing energy and material waste, is being shown here. Now, this intelligent warehousing system accommodates products of different sizes and shapes, and it can adapt to different workflows. Automation cuts manual process energy, and the system's flexibility makes sustainable digitalization accessible to smaller businesses. What we see here is a supply chain management. Again, you can see that inbound goods to outbound goods and everything in between can be modeled using the digital twin. We can use the real-time data capture and visualization. The movement of the goods are tracked inbound and outbound. and it's an agile, cost-effective solution with complete visibility and transparency across the supply chain. Productivity optimization. What you can see here is the operator movement, which I described in the previous slide very, very clearly. And then we see that at the areas marked near the separators is where there is a concentration of traffic. The right slide actually shows about how the product moves through the workflow. So the movement of the goods are tracked inbound and outbound, and also the people movement. Now, this definitely shows us that a layout optimization is required. Now, what you see at the bottom is the layout simulation, which was done using traditional time and motion studies. However, if we want to optimize the layout with current methodology, it is almost impossible. This means that the system has to be stopped. There is downtime, which is not possible with critical manufacturing. The current methodology of simulation allows us to do a what is scenario. However, digital twin enables us to do what if scenario. We can quickly change the layout and test for ourselves for optimization. Now we come to an automated quality inspection cell. The first picture on the top left shows a handheld scanner wherein an operator uses it. Then, of course, now with companies like the truck companies Iveco and others have made that process automated by fixing the scanner to a robot, which is a fantastic idea. However, this is not a cost-effective solution, especially for SMEs. If we actually have a look, we will find that the scanning process contributes to only 10% of the operations in a value chain. That means for 90% of the time, the robot is idle. And we have seen, if you recall, 1 liter per minute is the compressed air consumption of an idle robot. Every company is trying to maximize the usage of their resources. So, what if we had the flexibility to repurpose this robot into a mobile robot system by maximizing the payload design of the end effector control, having an autonomous and fully integrated workflow. This is also capable of accommodating products of different sizes by having different end effectors. As you can see here, we have done that. So, what have we achieved by this? The traditional inspection systems, the handheld scanners or the fixed robots are energy intensive and inflexible, contributing to 10% of the operational waste. A mobile autonomous robot with advanced scanning and lightweight end effectors reduce energy use and support mass customization. And there is an emphasis on decarbonization, energy savings from reduced idle time, eliminated transport by repurposing the robots to not only do the scanning but also transport the parts to the next station. So, what you see here is the cloud-based data, which was actually generated using Power BI, and we can see here in the next figure a bit more clearly that the green line shows that there is a high repeatability when we use the robot, and the black line is what is achievable by manual operation, and also reduced processing time. Again, green is what the robot can achieve and what can be achieved by manual processes. It gives a very clear indication of that. One thing of caution and something that we need to remember, that these innovations are not simple. It's a co-created solution between partnership between the industries as well as the universities. Only then we can achieve this type of unbrownfielding of legacy systems. We have integrated a man-machine interface cell, which is a symbiotic cell, to the cyber-physical system, which we had described before. The cyber-physical system was a completely automated system. By introducing the symbiotic cell, we achieve much more optimization. How is that? Because by integrating the humans, the dexterity of the humans and the problem-solving capability of the humans is now integrated into the system. As I mentioned in the first time, it's a real-time integration of humans, machines, and objects towards the management of systems. So the digital twin is used for virtual commissioning and optimization, and integration of collaborative robots and MES is manufacturing execution systems and the human-machine interface. Collaborative robots work alongside the humans with precision and guided by the MES for real-time monitoring and control. This enhances the resource efficiency, reduces downtime, and supports the use of renewable energy, all contributing to decarbonization. Let us see how we can apply predictive analytics to an integrated cyber-physical system, which was described before. What we observed was that the actual throughput was marginally less than is predicted by the digital twin. On doing the data analytics, real-time data analytics, as you can see in the figure, that the RFID system failed to read the actual carrier correctly. You can see that it is skipping the carriers. The physical system is reading carrier number 6, whereas the digital twin read carrier number 4. This was due to a timing error in the station stopper. It is a software-related problem. The carrier ID is supposed to match the digital twin, but it is not. The interesting point is that this is not detected by the system, because if the carrier does not stop at a particular stopper, it will just go around in the conveyor belt. So it's not an obvious error that can be detected by humans, but the real-time data analytics helped us to do that. And actually, what had happened was that there was an error in the code, which was then set right, and it was happening not regularly, it was happening in an intermittent fashion, and that made it very, very difficult to identify. So a problem which could not have been identified without the digital twin, digitalization has helped us to do that. Now, we can apply the smart sensing and historical data to trace other causes of defects and inefficiencies, and regularly run simulations and data analysis to detect and address root causes proactively. The other problem that we found was, as you can see in the figure, that the actuators are giving two different values. One is 83 milliseconds and one is 125 milliseconds. This actuator information is showing discrepancy, and this is directly related to the air pressure, conditions such as cold start, environmental conditions, and so on and so forth. All of these information can be recorded in the cloud and can be used for root cause analysis at a later time to identify which sensor is reaching end of life, for example. What are some of the challenges that we are facing in digitalization? Number one is high initial costs, infrastructure needs. There is also the question of data privacy and cybersecurity. The energy consumption of digital systems, example data centers, is very high. As an example, actually, I recently read that the artificial intelligence data centers they generate so much of heat that they are inclined to be located in very cold countries like Sweden. The other technology challenges which most industries are facing today is legacy system and brownfielding, workforce upskilling, cost and scalability, and again, cybersecurity features in every part of the cycle. By 2030, digitalization could cut global emissions, and the need for IoT, quantum computing, and digitalization is very essential. We have shown by these use cases that if harnessed properly, digitalization can prove to be one of the greatest tools for decarbonization.
Last 10, 15 years, we just was focusing on the improving efficiency in the manufacturing. But now we realize that efficiency is not important for now. So decarbonization is very important because every process or every product what we are doing is generate a carbon footprint. And digitalization very important part of it because it's enable us to understand what is the carbon footprint we are having during the whole life cycle of the products, which means it includes all the supply chain process.
In the future, I would say you won't be able to see a battery. So we call it as invisible battery. So the structures will be doing the job for that. So structures can act as a battery. Structures can detect its own health and provide you information. Just imagine you have your electric car and it's saying like, hey, I have a small crack in it, fix it. It's the easy way. So likewise, here we can make these structures functional. You can get that structural information on a day-to-day basis, real time. That's the way we are focusing more towards high-tech sectors like aerospace, defense, even space sectors.
My parting statement would be that digitalization is not just a tool, but it is a catalyst for decarbonization, empowering industries and societies to achieve climate neutrality while fostering innovation and resilience. Let's leverage technology to build a sustainable tomorrow. Thank you.